Right, hello and welcome to the Physoc revision session for Physics 1B. This is particularly for the special higher Physics 1B. So if you're rewatching this in the future for a normal version of that, then just bear in mind that special relativity isn't in your exam. But for special 1B kids, we're going to do a special relativity question. So let's get started. I will share my screen now. All right, sharing that, getting out of Phys 1A, onto Phys 1B. There we go. All right, so let's start off with special relativity, get that out of the way. So basically all of these questions from past papers were pretty much just a few nice questions with your basic Lorentz transforms or different frames of references. So they will be pretty straightforward, and then there's always one that's like a little bit dicey. So question one, part A, in a distant future, two space explorers are setting out to explore the galaxy. Sasha sets out with 0.6 c. We're going to ignore the time it took her to get to that speed. And this is as measured from the home planet. And then Desmos is going to travel in a perpendicular direction at 0.8 c. So part I, according to Sasha, her ship is 100 meters long. How long does an observer at home, how long does an observer on the home planet measure it to be? So basic transformation of length. So our formula for that is the length in this weird frame. So the viewing frame, that's that's viewing the person. So it'll be our home length is going to be equal to our rest length, or the length it's going to be in the same frame of reference. And then timesing it by our standard square root of 1 minus v squared on c squared. So our length, contracted length, is going to be equal to 100, the rest mass that Sasha observes her ship to be, 100 meters, times it by 1 minus 0.6 c squared over c squared. Of course, our c's cancel out. It's just equal to 100 square root of 1 minus 0.6 squared. And this ends up as 80 meters long. So first question, not too hard, just applying our formulas there. So the next part, Sasha's ship has a mass of 3 tons. What is the kinetic energy of the ship according to an observer on the home planet? So our rest mass is 3 tons. So converting that into kilograms, it's just going to be 3,000 kilograms. And our kinetic energy, as observed from the home mass, is going to be equal to, or as a result of the home planet, is going to be 1 over square root of 1 minus v squared over c squared mc squared. That is our formula there for our energy or our kinetic energy as a result of this mass moving close to the speed of light. So chucking in all the values for that, we have 3,000. So this was going to be 0.6 squared, 3,000 c squared, and this gives me 3.375 times 10 to the 20 joules. So again, it's just taking formulas pretty much from the notes or the formula sheet and putting in the values there. I guess the tricky thing is just to always remember which one is the transformed value and which is the rest value. So yeah, I guess that just comes with practice. Then part 3 of this, according to Sasha, what is Desmos's speed? So we remember that Sasha was going, say, in this direction at 0.6 c from home. And Desmos was going in a perpendicular direction. So let's call this y and x. And he was going at 0.8 c. So let's call this the y direction and the x direction. And we want to figure out the speed of Desmos according to Sasha. So Sasha is going to be our frame of reference, and Desmos is our object we're observing. And basically just looking at our equations for the velocity of an object as observed by a moving frame of reference. So because we also have this perpendicular distance, we need to find the x component and y component of those velocities. We cannot just straight up find one value there. So let's start off with the x component. So for this question, because our frame of reference is moving in the x direction, v of x is going to be equal to, v of x dash. So this is going to be our x velocity of Desmos according to Sasha. Is equal to v of x minus v over the square root 1 minus v of x over c squared. This v is our velocity of the frame of reference. So in this case, it's going to be Sasha's velocity from home, and then v of x is going to be the, value of x velocity of Desmos. And these are both according to home. So just some spicy relative velocity equations. And solving that, this is just 0 minus 0.6c over the square root of 1 minus v of x is again just going to be 0 because Desmos isn't moving in the horizontal direction according to home. Home only sees him moving vertically. So this just becomes negative 0.6c, and that makes sense because Sasha's moving 0.6c in the positive x direction. So relative to her, it just looks like Desmos is moving negative 0.6c basically in that direction, just because of relative velocity. So just the horizontal component there. Then let's look at the y component. And this is where it gets a little interesting. So the velocity in y dash, so y velocity of Desmos according to Sasha is equal to the square root of 1 minus b squared over c squared times by over, no square root on bottom, 1 minus, I think that is not correct. Is that meant to be a square root here or not? I don't think there is. I could be wrong. I've written it.
I don't think the formula doesn't, at least the formula we've got on the formula sheet doesn't have a square root.
Yeah, cool. Yeah, that's right then. Okay, excellent. Didn't particularly matter for that one, so I didn't pick it up there. But yes, that is absolutely right. Thank you. So then this is 1 minus bx over c squared. Alrighty, so of course our v is just our frame of reference velocity. This is our velocity in y of Desmos according to home. And I should note that this is also still in the x direction. So these are using the equations derived for velocity components in different directions as a result of a moving frame of reference in x, which is why this form looks different to the original one. And yeah, that's pretty much all we have. V of x is of course still Desmos in x according to home. And so just chucking all those values here, it's going to give me 1 minus 0.6 squared times 0.8c over 1 minus, again, this is 0 because Desmos doesn't move in the same direction as Sasha. So this just becomes 0.64c, the dy dash. So our total speed according to Sasha for Desmos is going to be just Pythagoras theorem, just adding up our vector components together, is equal to 0.877c. All right, so that is the end of that part. Essentially, this question was just using those formulas for the special relativity, and then it's just figuring out which values go in what. So hopefully that was pretty clear there. And yeah, the initial questions there in case you wanted to take a sneaky screenshot. And then part B of this special relativity question was looking at our space-time kind of diagrams. So in frame S, event B occurs 6 microseconds after event A, and then the change in distance is 5 kilometers from event A. How fast must an observer be moving along the x-axis so that the events A and B occur simultaneously? So we're just considering one-dimensional space-time, well, one-dimensional in space for this, and we want to figure out what our time contraction must be as a result of those Lorentz transforms. So let's go over here, part B, part I. So just drawing a little space-time diagram. A is going to be at this origin here, and B is somewhere over here where we have our change in x is equal to 5 kilometers, and our change in time was equal to 6 microseconds. So the time at A is equal to, position of A is equal to 0, and when we're contracted in as a result of moving close towards the speed of light, the contracted time and the contracted length is also going to be equal to 0. We're still going to stay at that origin point even after we start doing the weird space-time thing. Our original time for B is equal to 6 microseconds, and our original position from A to B, or our initial coordinate for B in space, was 5 kilometers, and so we want some velocity that's going to give us our transform time of B, event B is equal to 0, and our transformed position of event B is also equal to 0. And we're essentially just going to be using our Lorentz transforms. T dash is equal to 1 over root 1 minus b squared over c squared, b minus bx on c squared. So according to our x-axis, and then transformed for x, 1 over root 1 minus b squared over c squared, x minus bt. Actually, sorry, we don't want this. We just want it to be at the same time. So that can be whatever. This is what we want. So let's use this equation here. So we want our transformed time B is equal to 1 over root 1 minus b squared. That's what we're trying to find, our velocity, over our initial, timesing it by our initial time for event B, minus the velocity, stopped making marks, there it is, times the velocity we're going to be moving at, the initial position of B over c squared. So that's going to be 0. This term doesn't matter because it's going to be 0 anyway, times by 0 anyway, GB minus bxb over c squared. And so this gives us our, we want the time of event B from that initial origin or event A is equal to our velocity xb over c squared. So B is just going to be equal to c TB over XB. Oh, let's put that B over C so we can get some velocity in terms of C. And so just chucking in those values there, we end up with B is equal to 0.36 C. So this was 3 times 10 to the 8. TB was 6 times 10 to the negative 6. And this was 5 kilometers. Alrighty. Then part 2 of that question is it possible for event B to precede event A for some observer and justify our answer? So, yes, it is possible. And I guess the explanation is pretty much just in your notes. So it's just like revising that. But the basic idea is that to justify your answer, you could give an example calculation. Let's do this over to the side, actually. The part I'm going to say yes, and then to justify, we could give an example calculation where you can show that E dash is equal to a negative value, or we could just, I don't know, revise or like spit out some sort of definition and say that for this event to precede event A, we would have to have our velocity of the events, or our change in X over change in T to be greater than our speed there. So that's a little explanation of how you would answer that, but I did not make notes for that. So that's as far as we're going with that question. Yeah, special relativity, it's a bit wacky to wrap your head around, but the basic idea is just this kind of method of going through using the equations on the formula sheet, which I believe you will be given. Yeah, and then just remembering which values correspond to which terms in the question. All right, so that is our special relativity question. I'm gonna skip the Gauss's law one that I had just for the interest of time and go to this capacitors one, just because it also has Gauss's law. I just didn't know how much time I was gonna have. All right, so this is a little bit of Gauss's law and a little bit of capacitance. So we have 2 concentric metal cylinders, as shown in the diagram. They have a length L, and the inner cylinder has radius RA, and etc. They give us all these definitions of the radii values here. And they've told us that the inner cylinder has a linear charge density of 3 lambda, and the outer cylinder has a linear charge density of lambda. And we've just got this finite cylinder here. So part A, describe the charge density on each surface. Honestly, not entirely sure what they wanted for this question, but as we move on, it becomes a bit vague as to whether our linear charge density is in terms of the circumference or in terms of the length of the cylinder. So I think this part A is where you state your assumption of what you're going to be using in your calculation. In my case, for part A, I'm going to say that we have 3 lambda, I guess, or whatever the charge value is. So 3 lambda charge unit length of the cylinder. So our total charge on, I guess, the inner cylinder. Oops, cannot spell. So say, let's go Q inner is going to be equal to 3 lambda times L, where our initial linear charge density is, of course, just like charge per length. And then total charge on the outer cylinder because it told us that on the outer cylinder, we have a linear charge density of lambda. I'm going to call this Q outer is equal to lambda times L. Because it says describe, makes me think that they kind of want more details about what really happens with a metal sheet. But yeah, bit ambiguous for that question. You can probably put as much or as little detail as you want or have time to do for what you know about charge distribution in a metal. But just because it's vague later on, I think the main idea is that you state what you're going to be using or state what you assume the per unit length is. And my idea is that there's going to be 3 lambda for each unit length as we go down through the length of the cylinder, rather than per unit length around the circumference. That would be a bit of a pain to do the maths for. All right. So for part B, now we're going to get into the maths of it. So we're going to derive an expression for the electric field at radius RB to RC. So this is going to be this internal bit here between the 2 cylinders. And we're going to show all working and justify all steps. So part B, this is RB, and this is RC, very simplified drawing here. And because we were just talking about how the charge is distributed on the surface, we can just use Gauss's law. We'll take a Gaussian surface in the region we want to look at, and because it's a pretty symmetric shape, pretty straightforward that our Gaussian surface is also going to be a cylinder with some radius r, where RB is less than R is less than RC. And that's going to be able to give us our expression for the electric field in that region as a result of the enclosed charge due to the charge distribution on the inner surface. So Gauss's law, we have this surface integral of our electric field with respect to the area is equal to our enclosed charge over permittivity of free space. So our enclosed charge is the charge on our inner cylinder, which is just equal to 3 lambda times L from part A. We're also going to assume a constant electric field for each R as a result of our constant charge density. So there's no particular reason why our electric field would vary along this area here. We're going to assume that for each, I guess, circular cut, or yeah, each kind of ring we take in this region, we're going to have a constant electric field around that ring, which means we can take E out the front of the integral. Again, because this question said showing all working and justifying all steps, you could go into as much detail as you would like, but I think the bare minimum would just be to explain each step or clearly have each step of the working out. Don't skip any steps or try to do any funky calculation-y things from your notes, or take a result from your notes. I'm not quite sure how much leeway you have with looking at your notes with this exam. But yeah, just show you're working out as much as possible. And if you think it's not clear, then have some written explanation. All right. So I've said we can take E out the front. So we have E over the closed integral of the area is equal to our enclosed charge, which is just now 3 lambda L over our permittivity of free space. This just becomes the area of our Gaussian surface. We might actually have to explain why we took this. So Gauss's law take cylindrical Gaussian surface due to symmetric system. Yeah, cool. And so our area of our Gaussian surface with a radius r that's somewhere between RB and RC, and a length that's equal to our cylindrical surface. This just becomes E is equal to, E times 2 pi RL, our surface area of that cylinder, over 3 lambda L over epsilon naught. Cancel out the L's and take 2 pi r to the other side. So our electric field is 3 lambda over 2 pi r epsilon naught for the bounds of r. That is essentially the end of that part there. So just using Gauss's law to figure out what our electric field is in that region. Part C, sketch a graph showing the electric field from r is equal to 0 to r is equal to 3 times RD. And we're going to have to include as many details as we can. All right, so part C, let's redraw our kind of surface here. Actually, we're going to need all our radius details now. All right, so RA, RB, RC, and RD at the end. And we'll have a big graph up here. And so from 0 to RA, so just this internal bit here, there's no enclosed charge. Which means that if we had done Gauss's law, our electric field would be 0. For the next part, we have from RA to RB, in color. This is inside our first cylinder. We know it is metal, so there is no internal field. So E is still equal to 0 for this part. For the next bit, RB to RC, this is what we found in part B, which is our electric field is equal to 3 lambda over 2 pi r epsilon naught. And let me call that in just for completion there. Then the next little section, pretty much the same as the other blue section. We're inside the metal now. For RC to RD. So our E field is 0 again. And then on the outside, let's just make that black, from R is greater than RD and onwards, our surrounding region here, pretty much taking the same sort of approach as part B before. We're going to have to take a Gaussian surface all the way around both our cylinders and figure out what the E field is as a result of our enclosed charge. So we can quickly do that. Our Gauss's law. This time our electric field, we know it's constant, and we know our area of our Gaussian surface is just going to be the area of the cylinder, 2 pi r L. Our enclosed charge is going to be the charge on the inner surface plus the charge of the outer surface. So adding these values together, we were also told that they're just these positive values at the top here. So they are going to add together. They're not going to subtract. So this is a total of 3 lambda L plus lambda L. over epsilon naught. The L's obviously cancel, and we get E 2 pi r is equal to 4 lambda on epsilon naught. And so our E field is equal to 2 lambda over pi r epsilon naught. Alrighty. And so that's what our electric field is going to be from RD, well, from R greater than RD. So they want us to do it up until 3 times RD. So let's put this on our little thing here. Let's mark out some points, RA, RB, RC, and RD. We know it's going to be, let's red marker for this line. We know it's going to be 0 up until RA. It's going to be 0 between RA and RB as well. It's also going to be 0 between RC and RD. Then looking at our region between B and C, we've got a hyperbolic relation. So it's going to be our electric field is equal to some constant times 1 over R. So let's just block out a little hyperbolic line here. Probably gonna have to go down steeper than that. That's a bit weird. Yeah, possible. Really depends on how big R is and how big our charges are as to how steep this is going to be. Yeah, that looks like a convincing hyperbola now. So we can use this to trace out our section from RB to RC. And then from RD onwards, we have a similar sort of relation. It's just a different constant. So if we consider from, why is that right? There we go. From B to C, we had E is equal to 3 lambda on 2 pi epsilon naught R. And then from D onwards, its E is equal to 2 lambda on pi R epsilon naught. So this is equal to 4 on 3 times epsilon from B to C. So it's just going to be a little bit steeper of a hyperbola, or a little bit higher up, really. Again, we don't really know the size of these radii, whether this should go higher above our initial starting point or lower. But if I draw it out like this, then I can at least say that this point here is 4 over 3 times greater than what it would have been if we just had our initial line. And third. And spell that right. Anyway, that's probably as much detail as we can give. We can mark out a few other points. RD there. Like we could say that at this point it's going to be 3 lambda over 2 pi RB epsilon naught, and do that for a few other points. But it doesn't particularly tell us that much. I think the only distinction we need to make is how far up this goes, depending on the different radii. But that's essentially the shape of what this would be for the complete range of radii. Yeah, so I think just make your diagrams as clear as possible and as big as possible when you're doing these questions, and try to put in as much information as you can. Right. Part D, we're only halfway through the question. All right, so part D, derive the expression for potential difference between the two cylinders. So now we have the electric field between B and RC. We can use that to find the potential difference within that region as well. All right, so part D, we want potential difference. And between the two cylinders is going to be from RB to RC. And our potential difference, B, is equal to the integral of the electric field with respect to the distance. So in this case, it's going to be with respect to the radius. We're also going to be doing the integral limits between radius RB and RC. And so let's go ahead and do that. So from RB to RC, our equation for the electric field, this is just coming from our result for part B, is 3 lambda over 2 pi epsilon naught R B R. And take all the constants out the front. It's going to be 3 lambda over 2 pi epsilon naught integral of RB to RC over 1 over R. We of course know that the integral over 1 over R is going to be log of an R. So 3 lambda over 2 pi epsilon naught. The natural log of R from RB to RC. And this of course ends up as log of RB over RC. And that's pretty much as simple as we can get our potential difference. So just doing the integral of our equation there. So even if you mess up something and you can't get out the electric field, try your best to assume what the form of that would be, and then you could probably still get all the marks for this question by just taking the integral of whatever you have as the electric field. That's a pretty good tactic for when you can't get some particular part in a question and there's like 10 other parts to go. All right, so that was part D, our potential difference between those two cylinders. So part E, the charge density on the outer cylinder has now changed to -3 lambda. Does this change the potential difference between the cylinders? Explain why or why not. If it does change, derive an expression for the new potential difference. Does anyone want to have a guess as to if it should change or not, if we're just changing the charge on the outer cylinder? Who thinks yes, it is going to change? Or no, it's not? Take a wild guess. Or, well, probably an educated guess, but if all else fails, then a wild guess. No, yeah, I agree with you. It's not going to change because we found our potential difference from our electric field that we derived. And our electric field was just taking into account the enclosed charge of our Gaussian surface, which is just the charge on the inner cylinder. So if the outer cylinder changes charge, we don't really see it in the maths that we did. So all the way down, E, no, it does not change. Because our potential difference was dependent on electric field between RB and RC, and our E field was dependent only on charge on our inner cylinder, not our outer one. So our potential difference and our electric field between the two cylinders does not change at all if we change our outer charge. However, what does change now is that we have some sort of charge on one piece of metal, one plate of metal, and an equal and opposite charge on another piece of metal very close to it. This is, of course, just a capacitor. And so now we have this capacitor, we can derive an expression for the capacitance. We probably couldn't have done that before because it doesn't really make sense for the two plates of the capacitor to have different charges or to even have the same sign of a charge. But now it's definitely a capacitor, so we can use our capacitance equations and it's just chucking in the values into the formula. So part F, we want to find our capacitance of this two-cylinder system. And our capacitance equation is just C is equal to Q on V, where Q is our charge on plates. Doesn't matter, the equal and opposite would just take the positive one. And this is going to be our potential difference. which is great that we said before that our potential difference doesn't change. So we can just chuck in the value that we got for part D there. So our Q is of course equal to 3 lambda L, not just 3 lambda, that was only the charge density. So we got to times it by the length to get the total charge. And we're just taking the positive one because it doesn't make sense to have a negative capacitance, I don't think. So this is just going to be 3 lambda L over our potential difference, which was 3 lambda over 2 pi epsilon log of RB over RC. 3 lambda over 2 pi epsilon naught ln RB over RC, and cancel out 3 lambdas. And this gives us 2 pi epsilon naught L over log of RB over RC. And interestingly enough, the capacitance doesn't even care what charge is on these things. It only cares about geometry of the two plates. All right, so that is the end of that very long cylindrical capacitors question. Doing a bit of Gauss, doing a bit of finding the potential difference from an electric field. Are there any questions about that so far? I'm assuming we're all good, but feel free to chuck a question on the chat or unmute and ask a question. Keep in mind that this is recorded, so if you don't want your voice in the recording, then that's okay. But otherwise, we will move on. So that was a nice little intro into electromagnetism topic. Let's look at a magnetic field and inductance question. All right, so we've got 2 parts of a question here. I don't really remember which paper I took these from. I kind of just scrolled through a few and figured out which ones I didn't do on the revision session on Friday and was like, yeah, let's do that. So this first one is a Biot-Savart law question. And the reason why it's a Biot-Savart law is because there's no real easy symmetric shape to do ampere. Biot-Savart law is really our only option. So question B here. So we pretty much just have to break down this little circuit into its individual components and then apply Biot-Savart law to each of them. So we're going to have this outer radius RB here. The direction of current is to the right or clockwise direction. Then we're going to have this inner radius section of RA, this semicircle. This is going in the counterclockwise direction. And then we have our 2 straight line bits that are going with the current going towards the left there. So let's call this section 1. Can I get my pens back? Section 2. And lastly, our green section, section 3. And we'll just write out what our Biot-Savart law is. So dB, the infinitesimally small amount of magnetic field as a result of the tiny amount of wire, is equal to mu naught, our permeability of free space, over 4 pi, times our current, our tiny infinitely small bit of length, cross product with the distance r to the point in question from the current over r cubed. And we want to figure out from point P, so this is kind of like the center of our circles there. And we'll remember our right-hand rule to figure out the direction of magnetic field as a result of current. So it's like if you have your like thumb pointing up and then like your fingers curled around like this, it's perfect drawing, don't question it. This is our direction of current. This is going to be our direction of magnetic field. So at point B, the result from 1 is going to be into the page. And the result of part 2 is going to be out of the page just by aligning our thumb along the direction of the current and then figuring out if our fingers are going to be coming out of the page at this point P or going into the page. So this is just going to keep in mind for the signs of the different components. And then I won't tell you which way the magnetic field is going for part 3, because a bit of a spoiler, it's not going to make a difference. So our total field, just looking at the question, our formula sheet has R squared. Which one should we use? For the Biot-Savart law, that would be my mistake. Is there an R on the top of that? Let me Google it real quick. Yeah, that could be my bad. Okay, I think it's because I put like an R on the top instead of just the unit vector of R. All right, let me get this back up. Okay, so what I did is I had this was like a legit R vector, so it cancels out, but I guess the proper format is that's R squared, and this is only a unit vector, so it doesn't have a magnitude, it's just telling me the direction. We can use that version of that because that makes it simpler rather. So yeah, sorry, that's my bad. That's probably what we should use. I was kind of just going off what I was looking up on the internet when I was trying to solve these questions. But good spot, thank you for clarifying that. Okay, so let's put this into an integral form and figure out what's going on. So we're going to have our b is equal to our integral. We can take these constants out the front straight away, actually. Mu naught over 4 pi, big brackets. Let's do the integral part from part 1. So this is going to be our constant, our current through the section. And our current's pretty much constant the whole way through as well. We probably could have taken that out. Oh, well. There's going to be dl for section 1. This should actually be a negative. Let's make negative into the page and positive out of the page. Because we know they must oppose in some sort of way. So we'll figure out what our final answer is and then say if that's going to be in or out of the page. So that's for section 1. Let's of course cross R hat over RB is for section 1. Yeah, RB is our greater radius squared. And then we're going to plus for section 2 cross R over RA squared, just because we know it has to go in an opposing direction. And then the part 3, these lines go through point P, which means that the cross product from DL to R is going to be equal to 0. Just because there's no perpendicular distance between the point and the line. So our line 3 components, so these horizontal components of the current there, because they go through the point of P, like along this axis there, they're like radial components, they're going to have a 0 effect. So 3, no effect at P. If it was any other point, it probably would have an effect, but just because in particular we're looking at this point P that's along the axes of those wire components, it's just going to be 0. So this is part 3. Then just chucking in all our values that we need to solve this. Constants out the front, 4 pi, negative into the page is going to be I. DL, our total lengths that we need to account for, just to consider our limits, is going to be, I guess, from some sort of arbitrary 0 to the end of the circumference. So it's just going to be half of the circumference of a circle. So we can write that down. looking at our limits, length of semicircle is just going to be equal to pi RA or pi RB, depending on which one you're looking at. So this was section 1. And then we'll just say we go from 0 to Ender's length. So this goes from 0 to pi RB I dl over RB squared. Get rid of that. Plus, this goes from 0 pi RA I dl over RA squared. And I've gotten rid of the cross product with the unit vector just because at each point we can consider the radius of the circle, or the distance between any point on the wire to the middle of the circle is absolutely going to be perpendicular to, I guess, the very tiny, infinitely small length. If we consider it equal to like the tangent at that point, we know the distance from that is to the radius is going to be perpendicular. So a particular property of this circular wire is that our distance is always going to be perpendicular, just because we're considering that point in the middle of the circular shape. Again, if it was like over here, then we'd have to consider the straight wires, and then it probably wouldn't be perpendicular, and it'd be a bit of a nightmare to solve, but it is nice and simple. Well, not that nice and simple, but doable. That is the end of that bracket there. And then it's just, solving for those values there. So this becomes equal to mu naught on 4 pi I pi RA over RB over RB squared plus I pi RA squared, just solving that integral. And then this becomes mu naught over 4 pi I pi 1 over RA minus 1 over RB. Doesn't really matter how far we simplify it. They did give us values for RA, RB, and the current, and the value for permeability of free space is going to be in our notes somewhere. And so subbing that in, overall, our value of the B field is going to be 83.8 milliteslas. That was a positive value, and we set out of the page as positive, so it's going to be this magnitude out of the page. Cool. So even though RB had a longer length of wire, RA was close enough that it makes that more important contribution there. All right, so that's the end of question B. Just using Biot-Savart law, following through that integral and then putting in the values at the end. I think the only tricky part is just remembering that the different components, because the wires had current going in different direction, they're going to have to subtract. So just being clear what the final direction is, and making sure you account for the difference in direction as you go through, rather than just blindly adding them together. But that's Biot-Savart, pretty much just any wire. Usually they do give pretty nice shapes where you don't have to worry too much about it, but otherwise it'll be something more or less familiar and maybe complicated in the fact that you have to add up different components. But next we will look at part C of this question, just because part B was pretty short. So part C looks at a solenoid that's made of n circular loops, each with radius A and length L. And then a current with this oscillating sinusoidal current is sent along the solenoid. This is the current provided by the power supply, and the solenoid has a resistance of R. So part I, we're just using our Ampere's law to derive an expression for the magnetic field induced in the middle of the solenoid. And we're going to show all our working, including a diagram showing your Amperian loop and a statement of any assumptions that we're making. So let's go all the way down. Part I. We're going to assume, first of all, that B is the same everywhere in the solenoid. So if we consider like a cut section, it's not going to be different over here than over here, or in the middle versus the outside kind of thing. And then we're also going to assume that B field is equal to 0 just outside the solenoid. So this like immediate part here. And these are typical assumptions for a very long solenoid. And it's perfectly fine to just make assumptions to do your question, like within reasonable physical limits. Typical assumptions that your lecturer might make in derivations is perfectly reasonable to use those in the exam, as long as you state those assumptions and they didn't explicitly tell you not to. So we're going to assume our very long solenoid because that's typically how we do the derivation of magnetic fields in a solenoid. And so my loop that I'm going to be considering is this kind of cut section of the solenoid. So these are like my wires, and it's got a current coming out of the page. And this is going to be, oh, sorry, I'm going to take section. And this is my Amperian loop. And I'm going to assume I've taken it close enough that I'm assuming that I'm taking it close enough that there is no B field immediately outside. My current out of page. Just label everything red is my Amperian loop. They're an iron. Yes. And we'll put in some dimensions. This is going to be length L. And we're going to have our B field inside the solenoid in this direction here. If we imagine our right-hand rule swapping around those values, if we have like our thumb, our fingers curling around like this and our thumb going that way, it's drawing's getting progressively worse, then our current's coming out of the top and into the bottom, and our B field is pointing towards the right. So this is my little Amperian loop here, a bit of a dodgy drawing, but as long as we've labeled everything, it should be pretty clear what we're doing. And then we just got to solve that. So Ampere's law, our integral of the B field over a loop, closed loop integral of B with respect to L dl, our Amperian loop, is equal to our permeability of free space and our enclosed current. And our enclosed current is equal to the number of coils we're considering times our current that's through the wire. So this was the formula of the current that they gave us. And we also know that B is perpendicular to length at bottom. And then at the sides, B is perpendicular to our length of the loop, or dl of the loop. So therefore, B dot dl is equal to 0 at the sides. So these are some other statements that we need to make before we solve it. So as long as you're just like listing out all the assumptions or the steps you're making, then we're pretty good to go. And then of course, at the top, we've assumed close enough to coil, so B is equal to 0. Cool. So now we can just directly apply this to our Ampere's law formula. So accounting for all the sides of our Amperian rectangle, the sides don't count because the B field's going to be perpendicular to them, and the top doesn't count because it's close enough to the coil that there's no B field that's come back around there. So all we have is this horizontal length, and it's parallel to the B field, so we don't have to consider the cross product. And we're also going to consider that our B field is going to be the same everywhere in the solenoid, as we said, for a very long solenoid. So it's going to be a constant value along this length here, which means our closed path integral just dissolves to BL is equal to mu naught. Our enclosed charge is the number of coils we took into account times I naught sine omega t. That was our equation for the current in the wire. So this gives us B is equal to N I naught sine omega, omega t. Sorry, I forgot a mu naught. I didn't. I just forgot it in this line. Mu naught over L. And that is the answer for part I. Pretty straightforward, just making sure we state all the assumptions that we need. But otherwise, I think this is a pretty common derivation that you would have either done in your notes or in a tutorial. At the very least, there's definitely a lot of solutions for this kind of problem on the internet. Pretty standard for a long solenoid. So just remember to state all your assumptions and all the steps that you needed to take to simplify down the maths. I think that's basically the way of solving a lot of first year questions, just making sure you state the assumptions and then applying the maths. So part 2, write an expression for the current induced in the solenoid as a result of this applied B field. B field from the solenoid there. So inducing current, we're basically going to be looking at Faraday's law. And this is our voltage, or our EMF induced is going to be minus n the number of turns in the coil over the time derivative of our magnetic flux. Our magnetic flux is going to be equal to our area integral of B dA. We've assumed B is the same everywhere inside coil, so we can just simplify that to B times the area. And have they told us the shape of this solenoid? Yeah, and circular loops, each with radius A. So when we're considering our area of this B field, we're going to have our circular cross section with radius A, and it's just going to be pi A squared. So our magnetic flux is just going to be equal to our B from the question before, mu naught n I sine omega t over L, and our timesing it by our area, that's just going to be pi A squared. So now we chuck this in Faraday's law. Our EMF induced is going to be equal to negative n. Then it's going to be the time derivative of this value here. Let's take some constants out the front. This is going to be pi A squared mu naught n over L and I naught. And then it's just going to be d dt over sine omega t. Time derivative of the sine just goes to a cos, and we timesing it by the coefficient of the time out the front as well. So this becomes negative. There's two n's there, so we're going to n squared pi A squared mu naught I naught over L is going to be equal to omega cos omega t. And so finally, this gives me my induced current, my induced voltage, or my EMF, is equal to negative n squared pi a squared mu naught I naught omega over L cos omega t. Probably didn't need to write that out again. That's pretty much exactly what was there. And then going back up the top, just to remind ourselves what they were asking, part 2, we want to find the current that's induced in this solenoid. We found the EMF from Faraday's law, just any induced electricity in something as a result of a B field. They've given us the resistance R of our solenoid, so we can just use Ohm's law to get our current. So B is equal to IR, applies here for EMF. I is just going to be our EMF induced over resistance. That's an R. So it's just going to be negative n squared pi a squared mu naught I naught omega over L R cos omega t. And that is our final result for our induced current. Last part of this question, I've not left myself that much time for the second half of the course, but part 3, write an expression for the magnitude of the induced electric field inside the solenoid, a distance of R from the axes where R is less than the total radius of the coil. So still inside. So what kind of electric field do we get as a result of this induced current? So basically the idea is that there is no electrostatic charges inside coil. So if current was constant, then no E field, would get no electric field. Probably write this out in better English in the exam. It's too hard to talk and write at the same time. However, as there is a changing magnetic field, changing B field, we should get an electric field. Why isn't this right? We do get an electric field. And we're going to use same form as Faraday's law. Noting that our voltage is equal to our integral of electric field dl with respect to some sort of line integral, but we don't include the number of loops. So in this case, we're going to say our closed path integral of our electric field. In this case, we've got like our solenoid at the top here, and our path is going to be somewhere inside, and B field coming out of the page. E dl is equal to this EMF that we had before, which the format for that was negative d over dt closed integral of our flux, or B dA. Sorry, the important distinction here is, but don't include N. I think it's just going to cancel out on both sides. And we're going to let the path be some distance r from the axes, which is r smaller than a, which is the total radius of our solenoid. And so assuming that everything is constant, nothing weird's going on with the homogeneity throughout the internal structure of the solenoid, we'll just take out the constants. There's going to be E 2 pi r, the total length of this little surface, closed path loop there. And then this is going to be negative d over dt, of course, B times pi r squared. our area of our little path that we're considering there, of some little closed loop of this B field. And then this kind of turns out the same sort of way, except instead of A squared, we've got R squared for our little loop where we're considering our electric field. So E is equal to pi R squared n mu naught I naught omega over L cos omega t. Essentially just taking our result from before when we were finding our EMF induced in that. And we get the n back in from applying that B field. And that's essentially it. We also should include a direction because it is a vector. And so the idea is that E field must be clockwise. So induced B opposes original B field, just in terms of this diagram here. That is the end of that question. Cool. So that is the end of my electromagnetism questions. Kind of got 15 more allocated minutes for the second half of the course. I mean, we can go over time a little bit. Okay, let's look at optics. Does anyone have any particular preference between like some generic optics questions or something about Rayleigh's criterion? Any optics or Rayleigh's? What should we do? I think optics has a few more parts to it, but Rayleigh's has been asked in like the past 3 past papers, so take from that what you will. All right, Rayleigh's criterion, let's do it. All right, what's my notes? There they are. All right, so this has literally been in past papers from 2016 to 2018. I didn't even check the ones before that, but like consistently this same question. So question A, part A of Rayleigh's criterion, state Rayleigh's criterion and define all terms in the equation. So for a circular aperture, we have sine theta r is equal to 1.22 lambda over d, or just theta r is equal to 1.22 lambda over d, because it's usually a very small angle. And our terms in this question or this equation is theta r is going to be our like spatial or angular spacing between 2 objects that can be resolved. Lambda is our operational wavelength, depending on what device we're using. This is just like the average value that it uses. And D is our aperture diameter. There is also a single slit version, which is just that theta r is equal to lambda on D. But we typically use the circular aperture one because cameras have circular apertures and we're looking at optical resolution. And the general idea is that it's where the first minima of 2 images crosses. So whenever we're looking at something through a circular aperture or any kind of aperture, we get a diffraction pattern where we've got a maxima in the middle and then some minimas and maximas alongside. And so when we have 2 objects, we're going to have 2 diffraction patterns close to each other. So this is pretty good. We can resolve the two peaks pretty easily. Rayleigh's criterion is when the maxima of one is at the first minima of the other and vice versa. And so just resolvable. This is at the criteria. And then if it's any closer together, then our interference patterns are, well, they're going to interfere with each other, and we have no idea if there even are two objects sometimes. So it's just about where that maxima crosses with the first minima of the other object. So that is Rayleigh's criterion. Then part B, we're going to say, okay, we've got some sort of local real estate agent wants to take a photograph of properties from above. And she's asked me to calculate the spatial resolution she could achieve with a point and shoot camera, i.e. an ordinary photographic camera attached to a small unmanned aerial vehicle or a drone. So part B, I says, what parameters would we need from her in order to answer her question? So she's flying this drone up above some sort of suburb, and she wants to figure out what she needs from us in order to calculate what she can resolve. So if our Rayleigh's criterion is this, then we're going to need the diameter of the camera aperture. This is going to be our value D. We want to figure out our operational wavelength. And then depending on if she just wants the angular separation or the distance between two widths or how far up she can fly, then we might have to also ask for the width of the property or the flight range of the drone. So just these two if she wants the angular spatial resolution. This one if she wants how far she can take the picture from. And this one we would also need if she wants to figure out, I guess, minimum space she can resolve. All right, then part II says assume reasonable values for the parameters you listed above and calculate possible resolution. So typical diameter aperture of a camera is about 4 millimeters, and operational wavelength, we're going to assume it's just invisible light. So it's like 400 to 800 nanometers. So I'm going to just calculate a possible like average resolution and go, let's just make this 600 nanometers. You could calculate for both extremes of the visible light spectrum and then give a spatial resolution range, but I'm just going to calculate the average. So our average spatial resolution that she could get from this camera is going to be equal to 1.22. Our wavelength, 600 times 10 to the negative 9 nanometers over my aperture of the camera. It's going to be 4 times 10 to the negative 3 millimeters into meters. And it's going to be a spatial resolution of approximately 0.000183. This is, of course, just the angle. We could also give a reasonable height for the drone to fly. So I guess a drone height might be, I don't know, is like 50 meters reasonable for a drone. Not entirely sure what kind of aerial vehicle she's talking about, but let's assume it's some sort of like regular drone that you see zipping around at the park and say 50-ish meters. In this case, our spatial resolution, oops, that's a weird drawing. Our angle is theta r. The distance we want to resolve, let's call that x, and this is going to be 50 meters. So theta r is approximately just x over that 50. So the width that we could resolve with this kind of camera at this kind of height is just going to be like, what is that? 0.00 times 50. It's like about 0.0915 meters. That seems concerningly small to resolve. Maybe that's like an incorrect guess for the kind of height that a drone can be at, but either way, that's the general gist of that. Then part III, using the same point and shoot camera, calculate the smallest distance on the moon that you could resolve. This seems dodgy, but that would be the angular resolution that you could achieve. Then for the moon, the distance to the moon, oh, it's because I put this in meters. Yeah, no, that's fine. I don't know. I'm leaving it. Then this is going to be 384,000 kilometers. And so our distance, we want to resolve some sort of x on the moon, and this is our distance to the moon there. Using that spatial resolution is going to be equal to some x over the distance from the moon. And so the x we can resolve is going to be about 70 kilometers using this point and shoot method. That is the end of that optical resolution question. All right, now the question is go back to the second optics question or do a bit of the quantum question. Any preference? Quantum? Yeah, fair enough. All right. Yeah, we can go through this quickly. All right, so part A is pretty much just a lot of like explanation-y questions. So just writing out answers as clear as possible and to the best of your ability. So part AI, a landmark in the development of quantum mechanics, was the discovery of the photoelectric effect. The principal revelation of the photoelectric effect was that the energy of a monochrome beam of light depends on only one quantity. What is this quantity? Basically, the photoelectric effect, pretty standard stuff. Honestly, remembering it from the lab kind of helped me more than the notes. But basically, this depends, energy depends on frequency. Then part 2, why was this finding surprising? It was surprising because it does not depend on intensity, which was contrary to what they expected. And I mean, it does seem a bit unintuitive that it doesn't rely on intensity of light, only just the frequency. Then part 3, write down an equation expressing the conservation of energy involving the energy E of the light, kinetic energy of the photoelectrons, and the work function of the material. And that is just E, oops, right. E is equal to K plus phi, where E is equal to energy of incident light. K is our kinetic energy, and phi is our work function. Basically just taken from the notes, this question, but it's nice to throw you a bone with some low brain questions. Part C, consider a quantum mechanical particle of mass m trapped in a one-dimensional box of width L and described by the wave function. So inside the box, Schrodinger's equation is equal to this equation 1 here. What are the boundary conditions on our wave function? And basically, because we have this 1D box, it's going to be, sorry, this is part C. Oh, I skipped B for this question. See, we have a one-dimensional box and we're going to have some sort of wave function inside it. And the boundary conditions at x is equal to 0 and x is equal to L is that our wave function must vanish at x is equal to 0 and x is equal to L, because we need to have continuity across even our boundaries. And the idea is that outside of this well, we have a very high potential. So we have no wave function, or our wave function is equal to 0, which means we need constant, like a continuous kind of curve. Goes up and then comes down. So at our boundary conditions on the sides of the wall, our wave function must go to 0. So it's continuous with them. The walls, there's nothing there. Same kind of idea as we go along. We have our little wave function in the middle, but on the outsides or at the boundaries, it must go to 0 again. Just because this infinite potential, our wave function is forbidden there. And we can't just have it like randomly cut off because quantum physics only likes the nice things. Part 2, the wave function for the nth level has the form of our wave function psi is equal to a sine of n pi x on L, where n is the integer. What is the smallest allowable value of n? That's just going to be n is equal to 1, because it doesn't really make sense for n is equal to 0, because then our wave function is just going to be 0. It also must be an integer because quantum is called quantum because everything's quantized. Then part 3, show that our wave function is given by equation 2 satisfies Schrodinger's equation and use this to find the energy of the nth level. So this is basically just treating this to fit it into that. So taking the second spatial derivative. So this is triple I for this section. So our wave function, they've given it to us, which is nice, is equal to a sine n pi x over L. So our spatial derivative of that, our first derivative over dx is equal to a n pi on L cos n pi x on L. And then our second spatial derivative is just going to be negative a n squared pi squared over L squared, back to a sine by x over c, which is of course just equal to negative n pi over L squared sine, sine n pi x over L. Try not to make these look like c's. And then putting that into our Schrodinger's equation from equation 1 here, we have negative h bar squared over 2m, our second spatial derivative of the Schrodinger's equation. Are these partial derivatives? Yeah, they were. Is equal to negative h bar squared over 2m. It's actually going to be a positive now that we times it by this negative value, n pi over L squared a sine n pi x over L. Fit it in the Schrodinger's equation. This must be equal to E lambda, and it does because this, sorry, not lambda, psi, and it does because this was our original psi x. Therefore, our energy must be equal to h bar squared, n squared pi squared over 2m L squared. just by comparing it to the form of Schrödinger's equation. And then the last part of this question is finally use the normalization condition to determine what the amplitude should be. So normalization is generally the idea is that if we integrate between our boundary, it's like we're kind of like checking this, we're checking like the probability of our wave function or probability of our particle being somewhere in this box. And obviously it has to be in this box. It can't be outside of the box because that's the forbidden region. So our probability must equal to 1. So our integral in our boundary conditions of lambda squared, or officially like lambda star lambda, but that's only like complex conjugate sort of stuff, and it's all real numbers, so it's lambda squared, sorry, psi squared is equal to 1. And so this becomes, of course, dx. It's going to be a squared 0 L sine squared and pi x over L is equal to 1. To be x. This gives me a squared over 2 from 0 to L 1 minus sine 2 pi n x over L, just using my trig rules to simplify that, because I don't know what the integral of a sine squared is. Blah, blah, then that shortens itself down to, this just becomes L, and so we get a squared L over 2 equal to 1. So our amplitude is just equal to square root of 2 over L. This is just boiling down the maths. You guys are probably more familiar with how to do integrals than I am. But there we go. Also just using our boundary conditions that it must go to, our wave function must go to 0 at those boundary conditions there. So that is the end of that. Now to the normal laptop stage. I'm gonna stop sharing my screen. And that's all for today. This was recorded, so it'll be put up later. Thank you for joining me, and best of luck with your final.